Good morning students. Today we will talk about transformation of random variables, which is a very important subject in the context of probability theory. So, this is at least the problem is very simply stated. We have a random variable x, okay, distributed as some PDF p of x, okay, and I am just putting a label capital X to remind ourselves that this is a PDF of small x. Now, you have a function y that is given as f of x, okay, and this relationship is sort of a one to one mapping in the sense that I can invert this equation to get the values of x by simply saying that x is s f inverse of y, okay. And now I am interested in asking what is the PDF of y. Okay. So, basically I am asking that what is the value or what is the PDF of the distribution of y. So, let us call this distribution as p of y, and I am going to put a subscript capital Y to alert the reader that this is a PDF of y. Okay. Now, the problem is very simple to solve. In this case of a one dimensional random variable, you just have one variable that is x and it is mapped to another variable y. So, I can simply say that the probability to find a random variable in the vicinity of x is given by p of x dx, and since for each y each x there is a unique mapping, this should be the same as a probability to find the random variable y in the region y and y plus dy. Okay. So, then I can extract the PDF of y by simply p of x into mod of dx by dy, and this quantity dx by dy is called as the Jacobian of the transformation. So, it simply is a measure of a length amplification factor. In 2 dimensions, the Jacobian would give you an amplification of the area. In 3 dimensions, if you have 3 random variables, the Jacobian would give you a volume amplification factor. You are already probably aware of how to go from Cartesian coordinates x y to r theta coordinates. So, this would be like saying how does the area element, just a minor digression, dx dy is related to area element in plane polar coordinates. Now, the left hand side is an area element, it has dimensions of length square. If you look at the right hand side, it is just length. So, clearly something is missing here, and the something that is missing is the Jacobian of the transformation. So, I am just going to write down in general it is a function of the new coordinates in which I am taking my old coordinates, and I will discuss in the following lecture that this Jacobian is nothing but r. So, the 2 dimensional coordinate transformation from Cartesian to polar involves the Jacobian, that is r here. Now, you can say the area matches dimensionally on both sides, and the amplification factor is nothing but the radial distance r. which is the Jacobian of the transformation. And if the transformation between new coordinates and the old coordinates is canonical, then the Jacobian is unity. So, in this case the Jacobian is not unity, it is R, and this is the basically the transformation. So, you can also call the Jacobian as the area magnification factor. So, this is the 2 dimensional argument. In 3 dimensions you would basically have dx, dy, dz, and this will be equal to dr, d theta, d phi if you are going from Cartesian coordinates to spherical polar coordinates. Again we are running into the same issue that this is not dimensionally consistent. So, I must attach a Jacobian here, which is a function of, in general, a function of r, theta and phi. This will give me how the area element or the volume element in spherical polar coordinate is related to the volume element in the Cartesian coordinate. And if you do the calculation, which I will defer it for the assignment, this will come out to be r square sin theta. So, in some sense the Jacobian r square sin theta is the volume amplification factor of the coordinate transformation here. So, we are dealing with a one dimensional random variable. So, we do not have an area or a volume, we have a length. So, our Jacobian simply tells us how length is magnified. Okay. So, dx by dy is the Jacobian here, or the length magnification factor. So, I can write this as p of x dx into the mod of the Jacobian, because I do not want the probabilities to come out negative, the probability densities have to be positive. So, I have to guard it with this mod of j, and this will be my new probability density. So, this is going to be my result. That is as simple as it can get. So, we can take one simple example to illustrate the point. So, take this example of a random variable x, which is distributed as some lambda e raised to minus lambda x, and our random variable x is defined in the domain 0 to infinity. So, basically my PDF looks like this. So, if this is my x distribution, then it simply decays exponentially with this value becoming lambda. Okay. And let us say I define a function y, which is x square. Okay. So, then I have to find out what is the PDF of y. Okay. So, you can compute this PDF, which is basically, we will say that if y has a PDF P of y, then I can simply say that by conservation of probability, that P of y dy is equal to P of x dx. Okay. And by our previous logic, our P of y is nothing but the probability as a function of x into the Jacobian, which is dx over dy. Now, for the equation y equal to x square, we can compute this derivative. So, I can write down dx over dy as simply I can take derivative on both sides with x. So, I will with both sides with respect to y. So, I will get 1 equals twice x dx by dy. So, I can write this as 1 upon 2x. So, basically this is just p of x into 1 upon 2 mod x. Okay. Now, if you want to find out p of y, you can simply use the fact that x is always positive, it is defined in the range 0 to infinity. So, mod x is just x. So, I can rewrite the PDF of x as lambda e raised to minus lambda, and I will write x as square root of y. Okay. I will not take x as minus square root of y, because x is defined in the range 0 to infinity. Okay. So, I am going to take only the positive value of x, and I have in the denominator 2 times square root of x, because recall that my x was defined in the range 0 to infinity. Correction, this is square root of y. Okay. So, this is going to be my PDF, and if I plot this PDF, you can see that this has a singularity at x y equal to 0, because this PDF is lambda e raised to minus lambda y over 2 square root of y. Okay. So, as y goes to 0, the numerator goes to 1, denominator diverges to infinity. So, denominator diverges to 0. So, the PDF becomes infinity. So, there is a singularity at the origin, but it does not pose any problem. This is an integrable singularity, and by integrable singularity I mean I can immediately find out the norm of this PDF and show that this is well behaved. So, if you find out the norm, which is the conservation of total probability, since y is x square, you do not have negative values of y. Okay. So, the domain will be from 0 to infinity, y is x square, it cannot have negative values. Let us see that our PDF just obtained is well behaved or not. So, I am going to integrate this, and factor lambda can come out. Okay. And if I substitute square root of y as u, then I can just write down this 1 upon 2 square root of y dy as du. Okay. And the limits will transform from 0 to infinity to 0 to infinity, because that is the relationship square root y equals to u. So, I can write down that my norm is basically lambda times integral 0 to infinity e raised to minus u du, which e raised to minus lambda u du. Okay. So, then you can see that if you integrate this, you will get lambda into 1 upon lambda, which is 1. So, this PDF is also well behaved. So, our original PDF was, yes. So, let us write down the PDF. Our original PDF was lambda e raised to minus lambda x, and our final PDF is basically lambda over 2 square root of y e raised to minus lambda y, lambda square root y. This is going to be PDF of y. Fine. So, now let us proceed to a slightly more general case, that if you have a sum of two random variables, let us say you have x and y as two random variables distributed as p of x, and you have another variable y which is distributed as p of y, and you define a new random variable u which is x plus y, then you want to know how is this random variable u distributed. Okay, you are in possession of the random variable distributions x and y, you would like to know how is u distributed. Now, there are two ways of doing it. One way is the method of Jacobians that I will describe shortly. The other way is to attempt this problem by the method of characteristic functions. Both methods are will give you the same answer, but let us extend our present method of Jacobians in this this problem. So, going by the previous discussion, if you have the two variables x and y and you want to know how x plus y is distributed, you can introduce one more variable, let us say v, so that from x y you generate a new pair u v, which you can call as just x. Okay. So, what is happening here is that you have a PDF, I will say that this is an xy PDF of x comma y, and because x and y are independently distributed, this is nothing but I will say p of x x into p of y y. Okay. So, you have to find out by conservation of probability the distribution u v. So, we can just write down the probabilities to find the x y in the range x and x plus dx, y plus dy, such that the sum x plus y is z, or sum x plus y is u in this case. So, I am going to write down this as p x y x comma y dx dy, and basically this should be equal to the PDF u v u comma v into, now there is a amplification factor involved because I have gone from x y to u v du dv. So, this is a straightforward generalization of our 1D case. If you look at the 1D case which is written here, I had gone from x to y, now I am going from x y to u v. So, the area element dx dy transforms to area element du dv subject to a Jacobian, that is the area amplification factor. Now, this is very simple to derive actually. This if we derive equation 1, then the case is practically solved. So, you can think of some simple x y coordinate system wherein you consider two displacements dx and dy. Okay, so, this is displacement x and that is displacement y. Okay. And this is the small area that I would like to draw here. I will call it as area x y, or let us just call it area okay. And because our variables x y depend on variables u and v, I can write down x as a function of u and v, okay, and y as a function of u and v, or I can invert them and also write down equivalently that u is a function of x and y and v is a function of x and y. So, you can invert this map and then say that since a displacement in x is affected by displacements in u and v, vice versa you can say the displacement in u is affected by displacements in x and y. So, I will say that the displacement in x is affected by displacements in u and displacement in v. Okay. Of course, there are some prefactors here that one has to attach, so that it becomes displacement in x. These prefactors are dx over du and this is dx over dv. So, this is the total displacement affected in x due to individual displacements in u and v. Okay. So, I will rewrite this for displacement along y, then it is easy to see that this is just dy by dv times dv. So, now you can see that x and y were displacement, dx and dy were displacements in the x y plane, and that give me this small area element dx dy. So, the area element here is basically dx dy. It is simply obtained by cross product of dx and dy, but because dx and dy are orthogonal to each other, the cross product is just magnitude dx times dy. So, I can imagine now two displacements due to the uv pair. Okay, so, I will call the displacements due to uv pair as some vectors a and vectors b. The displacements due to x and y were dx and dy. So, you can already see the form of this vector a and b. If you look at the dx and dy, you can already pick up the form of u and v. Okay. So, you can see that the first term on the right hand side of dx is basically one term of a. So, I will say this is dx by du times du in the direction of I plus the component that is the first term for dy, that is dy by du times du in the direction j. Okay. So, as you can see, I can write down that this is entirely due to du. So, the displacement due to du has been has affected in my displacement vector A. Similarly, due to dV I can write down the other two parts, which is dx by dV plus dy by dV. So, this is basically due to dV. Okay. And similar to this area that was swept by the total basically the region dx dy, I can consider the displacement vectors A and B, the corresponding vectors. So, this is my vector A and this is my vector B. Their full forms are written already here. So, if you want you can project it along the x axis and get the x component, but that is not necessary here, the forms are already written before you. So, the same area which is in terms of dx dy becomes the area A cross B. Okay. So, I will wipe out this thing and indicate this area as some red color. So, this is basically the shaded region. So, I will say that this region here has the same area as the shaded region here. Of course, the area in the shaded region is given as A cross B, and I want the magnitude of the area. So, I have taken the magnitude of A cross B. That is the typical formula for area of a parallelogram with sides that are A and B. Okay. So, I will say that in terms of the coordinates, what I have done essentially is that I have transformed a rectangle into a parallelogram. Okay. So, either I can work in terms of x y, then my total area swept is dx dy, or I can compute A cross B, that is the area, both are the same. So, I will say that this is basically equal to the area of a parallelogram. Okay. So, I will say area of this is equal to area of the parallelogram. So, then I can simply write down write down this as dx dy, which is the area of rectangle, that was easy to see, as mod of A cross B. Now, mod of A cross B is nothing but I will write it as Ax by minus Bx Ay. Okay, that is the form of A cross B, which is in the plane coming out of the display board, and I have taken the magnitude of it. So, this is the strength of it. Okay. So, I can then write this as from this definition here, I can write it as dx over du into dy over dv minus, I can write it as dx over dv into dy over du. Of course, I have taken du times dv outside. Okay. So, then this can be written in the form of a determinant. the outer vertical line is for the mod. Okay. So, this is nothing but the Jacobian of the transformation. So, I will say this is basically I will say this is del x comma y over del u comma v, which is the Jacobian of the transformation times du dv. So, as the left hand side is basically dx into dy, that is my area element in the Cartesian coordinate, du dv is the area element in the uv coordinate system, the amplification factor is the Jacobian. Okay. So, now you can find out this amplification factor. So, now you can say that the probability density in the x y, which is a function of x comma y, times dx dy should be the same as the probability density in the uv plane for the variables u comma v into du dv. Okay. But I know the left hand side can also be written as p x y times the Jacobian into du dv. So, if I compare these two sides, okay, I can come to conclusion that p u v is nothing but p of x y into the Jacobian. Okay. The first and the third equality comes because of the Jacobians. So, if I just compare the second and third, I get this relationship, just knock off the area element du dv from both sides. So, then for a typical case I can solve this problem. So, let us call this equation 2. So, now we can apply this concept. So, you can take two random variables x that are distributed as x is distributed as some lambda into e raised to minus lambda x. Let us say that is a distribution of x, exponential distribution. Take another random variable that is distributed as some beta e raised to minus beta y, and you want to know how is the sum distributed. So, define a random variable nu from x y we call u v. So, u is a random variable of our interest, which is x plus y, and I will also get one more variable which is not necessary, but I want to evaluate the Jacobian. So, I need one more variable. Let us say v equals to x, we will keep it as x, we do not require it. So, we have kept it as x, you can keep it as y, you are free to do that. So, now let us compute the Jacobian. We have gone from x y to u v. So, therefore, the Jacobian dx over du into and dx over dv, dy over du and dy over dv. Okay. So, we can call this as equation 3 of a Jacobian. So, compute all these derivatives. So, dx over du we can write it as simply d over du into x can be written as u minus y. So, this is just 1, okay, and dx over dv is nothing but dx over dx, because v is equal to x. So, that is 1. Okay. You can write down for so, let me move it this place. Okay. So, we can write down dy over du as d by du of u minus x, which is 1, and we can write down dy by dv, which is dy by dx, because v is equal to x. Y and x are independent variables, so this is 0. So, therefore, our Jacobian becomes, so you can write down 1, 1, 1, 0. So, the Jacobian becomes minus 1. So, then we can write down our from our relationship here that p u comma v is equal to mod of minus 1, which is just 1. So, basically from equation 2 I can write down very easily that my u v distribution, joint distribution of u comma v, is given by the joint distribution of x comma y. But this is nothing but individual distribution products, because x and y are. So, now you can write down this as lambda into beta e raised to minus lambda into x into e raised to minus beta into y. Those are the forms of p x and p y. Okay. And let us substitute for x and y. Recall that our random variable u was x plus y, and we had taken the new variable v as just x. So, I am going to write down this as e raised to minus lambda v, because x is equal to v, into e raised to minus beta. I will write down y as u minus v, because x is equal to v. Now, this is the joint PDF of u comma v. I am interested in just the PDF of u. This can be obtained by washing out the v degrees of freedom. So, I have to wash out the v degrees of freedom, and this I can do by integrating my total PDF over v. The limits on v has to be carefully chosen. By looking at this relationship, I can easily say that the lowest value of v can be 0, because x and y are positive variables distributed between 0 and infinity. So, certainly u and v also will have the minimum value of 0. So, in this integral I have to take v as 0 as the lowest value. The upper limit on v will be definitely u, because by this relationship v cannot exceed u, because I want the sum to be x plus y, that is u. So, then I can write it as e raised to minus lambda v e raised to minus beta times u comma u minus v dv. Okay. So, then you can see that I will immediately take out lambda beta outside, and e raised to minus beta u will also come out of the integral, and I have v going from 0 to u e raised to minus v lambda minus beta. Okay. And then if I integrate this, I will get e raised to minus v lambda minus beta over beta minus lambda in the range. If I apply the limits, this will be basically lambda beta over beta minus lambda into e raised to minus beta u. Just plug the limits, the answer is very easily obtained, e raised to minus u into lambda minus beta minus 1. all right. So, then this is nothing but e raised to minus beta nu will cancel. What you will have for the first term is minus lambda mu lambda u minus e to the power minus beta u. So, this is the PDF of u. So, this is the PDF of the sum. So, this is how the sum is distributed. So, I will say this is the PDF which tells how x plus y is distributed. Okay. So, this brings us to the end of this variable transformation. You can also do similarly to just extend this method and compute how x into y will be distributed. So, you can take u as x y and v as y and then say how is u distributed by the techniques discussed above, can thus be calculated easily. Okay. So, we end the lecture here. We will in the assignment we will get some problems that will use different distributions. We have taken the example of the exponential distribution. You can generalize this method to compute other distributions as well. So, you can take x and y that are normally distributed and comment on how x plus y is distributed, x into y is distributed or x upon y is distributed. Please take care of the fact that when you are using the method of Jacobians, it will only give you an area amplification factor. Once that factor comes to your comes in front of you, you have to ensure that the joint PDF needs to be integrated over one variable to get the PDF of your interest, and when you do that, the integration limits have to be very carefully chosen. In this case, we had to ensure that v is not independently moving, it is moving keeping in the constraint that the sum x plus y is always fixed to u. So, that needs to be properly taken care of. Okay. So, we will stop here and proceed in the next class.